The diagram shows the electric field pattern around two charges. Okay, we are asked to add equipotential lines around these. Okay, so on the left we've got a positive charge and on the right we've got a negative charge, and they're going to produce a radial field pattern around them, and they're adding up to produce this pattern. So around the charge themselves, the equipotentials look like concentric circles, which are quite close to each other because the field strength is quite large closer you are to the charge. So the equipotentials are closer together. As you move further away, the equipotentials become further apart and actually stops being a circle and shape starts changing. And to figure out the shape of the equipotential lines, you need to ensure that you're drawing your lines when you joining them for the equipotentials, that they're always 90 degrees to the field lines wherever they meet. So if we continue with this, ensuring it's always 90 degrees whenever they intersect with the field lines, we get a pattern that looks like this. What about the values of the potentials themselves? So on the left, we've got a positive charge. And to bring a test positive charge from infinitely far away close to this charge here, we would have to do work because it will repel. So we have a positive potential on the left. While on the right, we'll have a negative potential because to bring a test positive charge close to a negative charge, energy will be released and you wouldn't have to do any work. So it's a negative work done there. Okay, infinitely far away, we know the potential is defined as 0. And also, so that means that around on the left hand side here on the next to the positive charge, it's going to be more positive as you get closer to the positive charge, and it decreases to 0 as you move further away. While on the right hand side, it's going to be more negative close to the negative charge, and is going to approach 0, is going to increase and approach 0 as you move away. Right in the center, because you've got equal charge on the left and right, the potentials from the left and right will add up to give you 0 volts. Now keep in mind the electric potential itself is not a vector, it doesn't have a direction, however it can add and subtract. Okay, if you put a charge in the middle, of course the potential here is 0, that doesn't mean the field strength is 0. If you put a positive charge in the middle, it will experience a force towards right. So keep in mind, just because the potential is 0 at some point, doesn't mean the electric field strength is 0 at that point. Okay, question 2. The diagram shows the electric potential around two charges. Okay, let's look at the diagrams. We've got QA on the left and QB on the right. So you got QA, you've got minus 30 volts right next to it, and QB, you've got minus 40 volts and next to it as well. Okay, we need to compare the two charges. So first of all, you can see the potential is negative around both of them. So that means the work done to bring a test positive charge close to it would be negative. So that's because it's going to attract that test positive charge. So we know QA and QB are negatively charged particles. And secondly, you can see QB is more negative the closer you get to it, more negative than QA. So that means that the charge of QB is greater. It's a more negative particle there. Part B of the question, we're asked to add some electric field lines. So we can treat those as point charges. So the closer we are to the charges, the more radial it will look. So a pattern around the charges, closer charge will look a bit like this, where I've ensured that it's 90 degrees to the potentials that have been drawn near it. Okay, and as we move further apart, the pattern changes slightly. And as you can see, actually, as what I've drawn so far is more lines around QB than I have around QA because I know QB has more charge. And as we move further apart, it looks a bit like this. Once again, I've tried to ensure that the potentials and field lines are 90 degrees to each other. Okay, now we add the direction onto this. So because these are negatively charged particles, any positive charge placed around them would be attracted towards them. So the field lines point inwards, like so. Okay, example 3. The graph shows the electric potential between two charged objects, A and B. Compare the two objects. So on the left, we've got object A, which has electric potential, which is clearly positive, and on object B has a negative electric potential. So when these two potentials from both these objects add up, we get this pattern here. So we know that object A had a electric potential pattern that would have looked a bit like this had it been on its own, because we know based on the equation of potential that potential is inverse proportional to distance. The graph looks a bit like this. While for charge B, it would have looked a bit like this. Okay, and together when they add up, they gave us this pattern. Okay, so let's start off with looking at the charges on the surface. Okay, the potentials on the surface. For object A, we can see it's a positive potential, so that means we know that charge A is positive, while for object B is negative, so charge B is negative. And for object A, the positive potential is larger, so that means that charge for A, and they're roughly the same radius as well, these two objects have the same size roughly, so that means charge A probably has a greater magnitude, so charge A is greater than charge B. Okay, and also we can see where they meet, the potential is equal to 0. That's closer to B than it is to A. So that also implies that charge A has a greater charge. Another way to analyze this graph is to use the gradient, because the gradient of a potential distance graph is equal to electric field strength. So let's look at the field strength on the surface of both of the charges. So if I draw tangents and on the surface of both of the charges A and B, the tangent is steeper on the surface of A because it's got a greater electric field strength on the surface of A. That's what we expect if charge A had a greater charge. Okay, and also I want to highlight here where V is equal to 0, where the potential is equal to 0, the gradient is not 0. So that means the electric field strength there is not 0. And that's a common misconception. People think with potential 0, electric field strength is 0. Is not the case. Okay, example 4 here, we've got a plus 6 E nucleus and a plus 2E nucleus. Complete the graph to show how the total electric potential varies with distance from the plus 6E nucleus. Okay, so again, using the graph around each charge, what had they been on their own, which follows this equation, inversely proportional to distance, the graph on the left would have looked positive and it would have looked a bit like this, and the graph on the right would have looked a bit like this. And you can see what I've done is I've made it shorter here because the electric potential will be smaller because it's not as charged. Okay, if I add these two together, the pattern will form something like this. Okay, let's just make sure this makes sense. Let's draw, because we know the gradient is equal to electric field strength on the surface of the 6E nucleus. It's got a steeper gradient than it does on the surface of the 2E nucleus, and that's what we expect because it's got more charge, so a stronger electric field strength there. Okay, and then there's going to be a point in between these two charges where the electric field strength is 0. That's where it's actually at this point. And notice how at that point the potential itself is not 0, but the electric field strength is 0 because the gradient at that point is 0.